Yeah, thanks for the kind introduction. And it's my great pleasure to be here today to share some of our latest research on efficient 3D perception for autonomous vehicles. So we'll have a Q&A session at the end of the lecture, but please feel free to interrupt me if you have any questions along the lecture. So all right, today's lecture will be centered around the three keywords in this title: efficient, 3D perception, and autonomous vehicles. So before diving into the technical parts of the lecture, so I would like to first spend like 10 minutes on explaining the three concepts. So what are the autonomous vehicles, and what is 3D perception, and why do we care about its efficiency? So let's first talk about autonomous vehicles. So I guess all of you are very familiar with this concept as you are taking this course, right? But I would still like to take a moment to quickly overview how the autonomous vehicles works. So as you can see from this video, the autonomous system actually can drive the car very smoothly in this fairly complicated scenario. There are a lot of things happening like in the autonomous system for sure. You can see it needs to recognize a lot of cars in this very crowded parking lot. It also needs to understand the behavior of other humans and other cars in order to react properly. For example, you can see like here, it has to pull over for the incoming traffic. That's actually not as easy. But the question is how it works. So this is the autonomy stack developed by Neural. So I use it here as an example. But like different companies are taking more or less similar approaches. So the first component in the stack is sensors. So they're essentially the eyes of the cars, gathering the information about the surrounding environment. There are a lot of different sensors mounted on the car. You can see here on top of the car, there are like 360 LiDAR and vision systems. And also there are radar sensors like all around the car, and also there are parameter vision system and the LiDAR system as well. So on the Waymo driver, there are in total 4 LiDAR sensors, 10 camera sensors, and 6 radar sensors. So that's a lot. These sensors can actually provide different kinds of information, and the different sensors of the same kind can also provide a better coverage of the surrounding of the car. So after collecting the information from the sensors, the system then goes to the perception module. So here it has to understand like what's going on around the car, for example, to recognize all the other cars and people and understanding the layout of the scene. So it's actually a very challenging task because you can see, for example, here, there are a lot of moving cars that are actually very far away from the eagle car. And also it's very hard to recognize them because of the low light condition here. And after perception, the system moves forward to the prediction and the planning module. So based on how other objects have moved in the past few seconds, so the prediction module will estimate how they will move in the near future, let's say in the next 10 seconds. And this is actually also very challenging because the future can be uncertain. For example, very close to the intersection, the car can actually either go straight or actually turn left or turn right. So the planning module has to take all these possibilities into consideration and then plan the movement accordingly in order to drive safely. And the final step is the control module. So it basically takes the planned trajectory and maps it into the action by actually controlling the steering wheels and acceleration. So I hope this gives you a very quick glance of how autonomous vehicles work. So in this lecture, we'll be mainly focusing on the second component here, the perception. So we're more precisely, we'll be focusing on the 3D perception. So what is 3D perception? The input to the 3D perception is the sensory data. For example, here we have the multi-view camera images from multi-view cameras here, and each having different orientations. For example, some of them heading front and some of them heading back and left and right. We also have the LiDAR point cloud here. So here I projected into the top-down bird's eye view for visualization purposes. So based on these inputs, the goal of the 3D perception is to understand the surrounding environment. For example, to do the 3D object detection to detect all the other objects in the scene, such as the cars, trucks, pedestrians here. So these detections have to happen in the 3D space because we care not only about these objects where they are in the 2D images, also we want to understand how far away are they from the eagle car. And in addition to detecting these dynamic objects, in some cases where we don't have the high definition map, we also want to parse the semantic layout based on the perception data. So that's called BEV map segmentation. So here we need to parse the drivable area, the lane divider, and the other semantic classes as well. So how can we achieve the 3D perception? So nowadays, all the 3D perception systems are mostly based on like neural networks, deep learning. So I will first briefly go over two of the very classic 3D perception models. One is a camera-based models, one is a LiDAR-based models. So first, let's take a look at the camera-based 3D perception model here. It's called FCOS 3D. So you can see the overall structure is actually very similar to the 2D detection models. For example, we have the image backbones at the very beginning, and then we have the feature pyramid network to extract the multi-scale features to cover objects with different sizes. The major difference here with the from the 2D detection is actually at the head. You can see here we not only care about the 2D offsets, the 2D locations of the car, we also want to regress the depths, the 3D dimensions of the box, and also like the orientations, and finally the velocity. So velocity is actually very important because it's used in the motion prediction stage to help the system understand like the movement of the car. And then it's this is the LiDAR-based 3D perception model. It's called point pillars. I think it's actually covered in the previous lecture. So most of the 3D perception models follows basically the same paradigm. So it will first use a 3D encoder here to extract the 3D features. And then it will project the 3D features down to the bird's eye view, a 2D map. So by the way, here, the 3D encoder they're using is very similar to a point net. It's less powerful than the sparse convolutional models I will introduce later, but it's actually like more friendly for the deployment, so they can be easily deployed using TensorRT, other acceleration libraries. And then for the BEVFusion map, because this is in 2D, so you can use any 2D backbones and detection heads to process it. For example, here they're using a multi-scale backbone and also using SSD as their detection head. So with the development of the deep learning and neural networks, we have actually observed a huge improvement in accuracy of the 3D perception model. So here is the trend of the 3D detection scores on the nuScenes leaderboard. You can see that the very first method here actually is point pillars that we just introduced. It only achieves around 45% nuScenes detection score. But over the past 4 years, the detection accuracy is improved from 45% to above 75% here. So that's a 30% absolute improvement. We are also witnessing more and more methods on the coming out each week actually on the leaderboard. It's a very fast evolving direction. However, the improved accuracy comes at the cost of the increased computation as well. So on the left-hand side, we have the latest YOLO V8 series. So that's a very popular efficient 2D detection models targeting real-time deployment. So you can see they are actually very efficient. While on the right-hand side, I listed a few representative 3D detection models in the chronological order. For example, the point painting, FCOS, and the latest transfusion and filter 3D. So we can see a clear gap in the computation between the 2D and 3D detectors here. So 2D detectors consume around 200 Gmax, while for some camera-based 3D detection models like BEVFusion, they're actually taking 3T max. So that raises a huge challenge for the efficiency side of the 3D detection models. So that comes to the third keyword in the of this lecture, efficiency. So one reason why we care about the efficiency is also the computers powering the self-driving cars could be a huge source of the carbon emission. So that's why we care about this efficiency. So this is the latest article from the MIT News. So a group of MIT researchers identified that the computers, so if we have 1 billion autonomous vehicles and each drives for 1 hour per day, and if it's mounted with a computer consuming 840 watts of energy, you can see its carbon emission is around the same as the data center currently do. So you can also see from the curves here. So because of this, the drive GPUs are actually usually more energy efficient than the server GPUs. For instance, a popular drive GPU here, the NVIDIA Jetson HGX Ring, it consumes only 40 watts of energy. So it's around 7 times lower than the server-side GPU like NVIDIA A100. But it also comes at a cost, right? So its peak performance is also weaker than the server-side GPU. For example, its peak performance is only 108 TOPS, while the server GPU A100 is 6 times more than that. So like the limited computational resources we have on the car also motivates us to design more efficient 3D perception algorithms. So that's actually the focus of this lecture. So for the rest of the lecture, I will start by introducing the BEVFusion. So it's a 3D perception framework that can efficiently support multiple sensors and handle multiple different 3D perception tasks. And next, I will give you a brief overview of our latest works, Platformer and Sparse ViT. So they're accelerating the LiDAR and camera encoders in the 3D perception models. And lastly, I will demonstrate how we have deployed our work in autonomous racing vehicle and also on a full-scale autonomous car. So let's begin with the BEVFusion. As I have mentioned earlier, like self-driving cars are equipped with numerous sensors, each with distinct types and also distinct orientations. So the three most commonly used sensors are the LiDAR, camera, and radars. So we'll first go over each one of them. So cameras are probably the most familiar sensors to all of us because we are using them on a daily basis. So they capture the dense RGB images in the 2D space, which can capture rich semantic information, for example, the color and the texture of the environment and the other cars. LiDARs, on the other hand, capture data in the form of a sparse 3D point cloud, which essentially is a set of points, XYZ coordinates, and sometimes we also have some other like features like intensities. So as the data is in 3D, the LiDARs can provide very accurate spatial information about the distance of each point to the ego car, which can be crucial for the 3D detection task. And this type of sensor has also become more accessible in the past few years. For example, the latest generations of the iPhone Pro actually has also equipped with the LiDAR scanners, which is underneath the camera sensors. And finally, the radars are kind of similar to the LiDARs in some ways. They are also capturing the data in the sparse point cloud format in the 3D or in the bird's eye view space. So there are two main differences between the LiDAR and the radar data collected. The first one is the data collected is much sparser than the LiDAR point cloud, and also it's much noisier. And also another thing is that the radar can directly measure the velocity of the other objects. That could be very useful if you're going to estimate the velocity of the other moving objects. So different sensors have distinct properties. Some of them are focusing on capturing the semantic information. Some of them are capturing spatial information, and some capturing motion clues. So using a variety of sensors can also improve the robustness of the 3D perception system. For example, the camera sensors are not very robust to lighting conditions. You can see from this visualization here, during the nighttime, the camera sensor can barely provide much useful information. While during the daytime, the direct sunlight can also cause overexposure, which also makes it very challenging for the camera sensors to capture anything. LiDAR sensors, you can see on the bottom of the two visualizations, are less affected by the lighting conditions. However, the LiDAR sensors are not very robust in some weather conditions. For example, here you can see in the rainy days, the LiDAR sensors will capture the water sprays in the data as well, which might actually confuse the 3D perception system and generate some false positive predictions. And the same applies to the foggy days. You can see that the fog particles can also generate some noise in the data. Well, in these two cases, the camera sensors are kind of less affected, and radar is actually very robust to different weather conditions. So therefore, fusing information from diverse sensors can help us avoid a single point failure from a single sensor and make the 3D perception system more robust. So one of the significant challenge in the sensor fusion is the view discrepancy. So that means different sensory data are in a different format in a different space. So for example, here we have the camera data. So they're in a perspective view, and we have the LiDAR data is in the 3D view. And also you can see actually different camera data, they're having different orientations. So that means if you're considering the top left corner of each camera sensor, they are not actually corresponding to the same spatial location. In order to understand the spatial relationship between different pixels across different camera sensors, we actually need to know how the cameras are mounted and using some calibration to understand the relationships. So that means we cannot naively just adding these features together and fuse them together, right? Because they are not actually corresponding to the same spatial location. So the goal of the multi-sensor fusion is actually to find a good shared space to resolve the view discrepancy issue. So there are two requirements here. First, the sensor data needs to be easily converted to this space without much of the loss of information. So here the conversion has to be implemented, can be implemented very efficiently and in a very easy manner. And also the information loss is another thing we need to consider because different sensors are giving us different information. We want to preserve these information as much as possible. And the second requirement is this space has to be suitable for different 3D perception tasks. Because in reality, we care not only about the 3D object detection, we also care about some other semantic tasks like the map segmentation. So now let's take a look at a few existing solutions. So the first solution is called camera-centric fusion. It's actually motivated by the RGBD data. So the basic idea is we can just project the LiDAR point cloud onto the camera plane using the camera to LiDAR transformation. And then you can see this is the sparse LiDAR depth we'll get. It's kind of different from the LiDAR depth, the depth we'll get from the RGBD sensor because it's much sparser here. And after that, we can just concatenate them together and we can process it using like any camera-based 3D detection models, for example, the FCOS 3D model I just mentioned. So what's the problem of this approach? So let's take a closer look at the LiDAR depth projected to the camera plane. So I circled out a few regions here. You can see that within each circle, right, there are clearly some points with like very different colors. So for some of the points, the depth is actually very small, and for some of them actually has a very large depth. So there's a discontinuity in the depth converted. The reason for that is when we are projecting the LiDAR point cloud to the camera plane, the depth value of each pixel is actually determined by the closest LiDAR point to the pixel. Therefore, like neighboring pixels can have different depths as long as they are closest to the different LiDAR point. So this will result in a loss of information about the true 3D structure of the scene and object, making it very hard to accurately detect and localize the 3D objects. And this could be an issue for the 3D detection task. So that's why actually most of the leading multi-sensor fusion 3D detection models don't really follow this approach. They're using a different approach called LiDAR-centric fusion. So the idea is that we want to project the camera information to the LiDAR space. So here is a very representative work called point painting. It's actually from the same group as the point peelers. So the first step is to run a 2D semantic segmentation to get the semantic labels for each pixel. For example, here we have the cars, we have the cyclists here. And after that, we paint the semantic labels to the LiDAR point cloud. So it will be a color point cloud afterwards. And then we can just use any LiDAR detectors to process it. For example, we can use the point peelers, we can use like sparse conv, like point RCNN to process it. So what's the issue of this approach? So the camera to LiDAR projection is actually very lossy in the semantics. So the camera and LiDAR feature, because the camera and LiDAR data have drastically different densities. So here you can see all these red dots are the LiDAR points projected onto the camera plane. So only 5% of the camera features are actually covered by one of the LiDAR points. That means all the other points, as long as they're not like visualized in red here, they're actually dropped directly during the decoration, the painting process. This is actually not optimal because you can see like the semantic information is very important for some classes. For example, if you want to understand the layout of the scene, that's definitely a necessary information you need to use. And also another thing we can notice here is the top right corner of this image is barely covered. So the reason for that is the LiDAR has a limited coverage in the range. For example, like plus minus like 50 meters. While a camera can actually capture objects that are very far away from the Eagle car. So if you're doing the fusion in this manner, if we project the decorate the camera features to the LiDAR data, all these image features, camera features will be directly discarded. That's also not optimal. So now we have talked about the limitations of like both camera-centric fusion and the LiDAR-centric fusion. Oh, okay. What's okay.
I just have a question. Have you used, or have you seen anything in the literature about using like intensity images or reflectivity images to do kind of these kinds of fusions?
So also projecting a LiDAR to a camera, right? So are you also projecting the LiDAR data to a camera using the intensity, like the depth?
Yes.
This is actually very similar to like the camera-centric fusion. So I haven't really seen a lot of papers doing that for the object detection specifically because the camera-based detection model, the accuracy actually lags far behind the LiDAR-based detection. So most people decided to like do that in the LiDAR space. But I think that's actually a very interesting idea because nowadays actually the camera-based detection catch up in the accuracy a lot. So that approach could be like interesting direction. Yeah. Yeah, so we have talked about the limitations of like both LiDAR-centric fusion and camera-centric fusion. So here comes the first small quiz. So like what other options do we have, right? How can we fuse the information better? We have the camera, we have the LiDAR. Is there a better solution for the fusion? Yep.
You could object space.
Object space.
Detection space.
Yeah, that's actually a very interesting idea. So some papers actually have explored that. So they use some sort of latent object queries, and then like they projected it onto either camera and LiDAR. That's actually a very interesting idea. It's actually very effective in the detection, 3D detection models. But if you think about it, if we care about the map segmentation, that could be very challenging, right? If you only care about those object using the object to query the different sensors. Yep.
Feature space.
In the feature space. So what kind of feature space are you thinking about?
You have a extractor for the LiDAR and another feature extractor for the image.
Mm-hmm.
You directly use the output like a latent space for both.
Mm-hmm.
You directly use those numbers to combine.
So that means that you have the camera features, LiDAR features, and then you do some spatial pooling, or
You just directly use so you can put techniques the output from two different feature extractors.
I see. So you flatten the features of like from different sensors, and then like use that as a fusion features. Yeah, I think that could be an interesting idea. I think, yeah. So some people will do like something a little bit more complicated, doing some like cross attention between the hidden features. That's actually a very interesting solution as well. Yeah. So actually, our approach is like already in the name of the paper. It's called BEVFusion, right? So basically, we're choosing the bird's eye view space. There are definitely other options, of course, like all these like object query, like the feature space, latent space could be a good alternative as well. So the reason we choose this space is first, like most of the 3D perception tasks can be supported in the bird's eye view space because like they're mostly like extracting features, attaching heads in the bird's eye view space. So let's take a look at how we can transform the features to the bird's eye view in a high level. So the LiDAR features is actually very simple because it's already in the 3D space. Projecting to the bird's eye view space, just discarding the z-axis, right? And you can see it's kind of preserving the geometric structure of the LiDAR because you can still see that this is a car, right? Even after projecting the height dimension. So in reality, we don't really directly discard the like height dimension. We'll do some like feature aggregation on the height dimension to embed it to the channel dimension. So in this way, the information of the Z is kind of still like preserved. Well, the camera is a little bit more complicated. I will detail in next few slides. But the overall idea is we have like multiple cameras. They are heading different orientations. We want to project it onto this shared bird's eye view space. Here, like front camera, back camera, and the other cameras as well. So from this visualization, you can have a very intuitive sense that like it's also very dense in the semantically dense. So preserving the density of the camera features. So after all the features are captured in the bird's eye view, we can easily fuse them together using some like element-wise operation. So let's take a look at how we implemented this. So given different sensory data, for example, we have the multi-view images, LiDAR point cloud, the radar targets. We'll first use a modality-specific encoders to extract their features. For example, here we are using like swing transformer, using ResNet as our camera encoders, using VoxelNet as our LiDAR encoder and the point pillars as our radar encoder. So after this encoding step, the camera's features are still in the perspective view, while the LiDAR and radar features are still in the 3D space. So next, we'll transform all these features in a unified bird's eye view space. So as I mentioned, the transformation process for the camera to bird's eye view is a little bit more complicated. So I will show it in the next slide. But for LiDAR radar, it's very simple. We just flatten it. So once all the features have been converted to the bird's eye view, we can just simply stack them together and then apply a BEV encoder to fuse the features together. And finally, we can apply multiple task-specific heads. For example, we can attach some detection, like center-based detection head for the 3D object detection, and some segmentation head for the BEV map segmentation. So now let's focus on the camera to bird's eye view transformation process. So this process can be a little bit abstract, so I will first provide you with an intuitive idea of how the process works. So to illustrate this transformation, so consider this street view image, right, of the schools of engineering here I found online. So this image is captured in a camera. From the camera, we can see it's in the perspective view. So the goal of the view transformation is actually to convert this perspective view image to a top-down map view image. It's very similar to the satellite image you can see here. So how can we achieve this? So the first step is we want to understand the depth of each image pixel. This is actually a very challenging task from the camera data because the camera doesn't really provide such information. So we follow the previous work to explicitly predict the depth distribution of each pixel. For example, you can see here, like for the pixel A, it has a large depth probability at a smaller depth, so indicating that this point is probably very close to the camera. While for the pixel C here, it has a large probability value at a larger depth, so it's probably very far away from the car. So this step is essentially a depth estimation process, so we can achieve this by just applying a few convolution layers to the image features. And next, we want to scatter each of the image pixels to a few discrete points. For example, here, like for each of the A, B, C, these 3 pixels, we want to scatter 4 points here. So in total, we'll have 12 points after the scattering process. So the feature of these scatter point will be depends on the 2 factors. One is the original image features here, and the other one is the depth distribution we just predicted. So the basic idea here is we just simply multiply these 2 factors together. For example, you can see the highlighted box here, the 2.5, is obtained by just multiplying the corresponding image feature here, which is 5.0, and the depth distribution here, which is the 2.5. So this results in so this completes the first step of the BEV to camera to BEV transformation. So in practice, after the downsampling, so here we will have around 3,000 image pixels. And for each of them, we will generate around 100 points. And because we have 6 cameras in total, so that means we'll generate a super dense point cloud, around 2 million points. So that's actually like 2 orders of magnitude denser than the LiDAR point cloud. So we need to keep that in mind in the next few steps because that could be an overhead. Yep.
The depth distribution, you get it from a monocam depth estimate?
Yep, just a monocular depth estimation. Sorry. So basically, like after the feature extraction, we just apply a few convolution layers together because we don't really need a very accurate depth estimation for this.
You're not using
No. We want to blend that into the original camera encoder. If we use a separate depth estimation model, it could actually introduce a huge overhead to the on the computation side. Is there any other questions here?
How do you get the number of image features here?
Oh, we use a camera encoder. For example, we use a ResNet to extract the features, and then we have features for all of them. Right. So, yep.
How did you get the number of features?
The number of point features. You mean like how many points we scatter, right? That's actually determining a fixed number. For example, for each pixel, we'll generate 1 point at for each depth value. For example, like 0, 0.5 meters, 1 meters, and all the way to the 6 meters. So there are around 120 points per pixel.
What happens when you end up with 2 points at the same position?
Yeah, that's exactly what we're going to handle in the next step. We want to pool, do some pooling, right? For all the features actually in the same grid. So it's not necessarily they're having exactly the same 3D coordinates, but as long as they are very close to each other, we want to kind of like aggregate their feature together into one feature. Yeah, so actually before that, we want to first understand like the association, actually like which are the points that are actually close to each other. So we do the grid association here. So this is an example of the point cloud generated after the scattering step. So for each point, we have a BEV coordinate here, and also we have a feature corresponding to that. So the way we generate a feature is just multiplying the image features and depth values. So for example, let's consider like the first point here with index 0. Its coordinate is 2.8, 2.6. So that means it falls into like this like blue grid. So it's a 10th grid. So you get a BEV grid index of 10. And the same applies to this one. The coordinate is like 3.8, 2.9. So it's actually in the yellow grid here, right? So you can do the same for all the other like points and get a grid index here. So this can be and then we want to reorder like all the entries in this table so that like all those points with the same BEV grid index will be consecutive with each other. So this step can be achieved by like doing an argument sort based on the BEV grid index, and then we just reorder all the entries based on the sorted rank. So this is the table after the sorting. You can see here the point index is no longer consecutive anymore. So this is basically the rank we will get. And although like this step seems very simple, it is actually surprisingly slow because sorting over 2 million entries using an argument sort is like a lot of computational effort, right? So, but there's one property we can leverage here to accelerate this process. So all the point coordinates here is actually fixed. If you think about the way it's generated, it's only based on the original camera grid the original camera coordinates and the transformation between the camera to the LiDAR. So as long as the sensors are well calibrated, for example, you have all the camera mounting known, and also you have the LiDAR mounting configuration known, then this is actually fixed. So the point coordinates are fixed, and therefore the BEV grid index is also fixed, and therefore the rank here is also fixed. So we don't really need to do the sorting during the inference time. We can just do that once, beforehand to store the pre-computed rank. And during the inference time, we can just use the rank here to reorder all the entries. Yep.
I thought that the coordinate is somehow derived as well from the depth of the point.
Because we actually generate a very dense point cloud. So actually for each of the depths, we will generate a point. Yeah, so actually, yeah, I think you are correct in some way, like that if you consider the, for example, for 1 pixel, the one with the largest depth is actually dynamic based on the depth prediction. But we're actually generating a very dense point cloud. The reason for that is we want to make sure this process is differentiable. If you generate only 1 point, so that means you're doing some sort of argmax over all the depth probability. But the argmax is not a differentiable process. So we want to use that as a relaxation to make it differentiable. Yeah, so this pre-computation optimization, although it's very simple, it can actually optimize this the latency of this step by a factor of 4. So now all the points within the same BEV grid will be consecutive to each other. The next step is to do some get a reduction over all the features within the same BEV grid here. So the reduction function we're using is just doing a summation. So for example, we can see here that for the first grid, the feature is 4. We can obtain it by 1 plus 3, right? So let's take a look at how to implement this. So aggregating the features within each BEV grid is actually not very straightforward because you can see that different BEV grid can actually have different numbers of points. So the existing implementation from LSS actually uses a very clever prefix sum trick. So basically, it first calculates the prefix sum of the feature here. You can see we get 1 and 4 is basically 1 plus 3 here, and 11 is 4 plus 7, and so on and so forth. We first get a prefix sum vector, and then after that, we just subtract the values at the boundaries where the indices change to obtain the reduction values within each interval. So here we can get a 4 here. 4 is basically subtracting an imaginary 0 here by from the 4, And the 4 here is subtracting 4 from 8, and 7 is 15 of 8 from 15. So you can compare the results here and here. It's actually correct. So this is a very clever implementation because it reuses a lot of existing operators in the, for example, in the PyTorch, in TensorFlow, for example, doing the prefix sum, doing the subtraction, doing the indexing. But the issue here is the prefix sum is actually not very efficient on the GPU. It requires a multi-level tree reduction to get it. And now, yeah, go ahead.
I thought it's quite
It's efficient, but if you think about it, like different outputs actually have the dependency between each other, right? If you want to get the prefix sum of the ladder element here, you need to first get the results before. So you need to do a tree reduction. So that's actually not, so it's not as efficient as, for example, just doing a sum. Yeah. And also, if you think about it here, there are a lot of unnecessary elements generated because what we only care about here is those prefix sum values at the boundary. So we're actually generating all of them just to support us to get all the the prefix sums at the boundary that we care about. So the way we accelerate it is also very simple. So we just write a specialized CUDA kernel. So the basic idea is we assign a GPU thread to each of the grid. And then within each grid, we just do an interval reduction and then write it back to the GPU. So it's very simple. But it turns out it's actually very effective because it removes the dependency between different output values. And also it does not require these like unnecessary value computation, right? So this optimization step can accelerate the whole process by a factor of 250 times. So the initial camera to bird's eye view transformation step took around like 500 milliseconds here. With the interval reduction, it can be accelerated by a factor of 22 times. And then further with the pre-computation, this step is optimized by another factor of 2. So you can see originally, like for the view transformation, so the right-hand side is the end-to-end breakdown, latency breakdown of the BEVFusion model. So 83% of the total runtime is actually spent on the view transformation process, a clear bottleneck. While with the optimizations, we can reduce this part to only 12%, achieving a 5 times end-to-end speedup. So this improvement is actually very crucial because if we want to unify the multiple sensory into a unified BEV space, this transformation is actually a key operator to achieve this. So now let's move on to the evaluation part. So here's a demo of the BEVFusion running on the nuScenes for 3D object detection and for the BEV map segmentation. So you can see that like the BEVFusion is able to recognize different objects fairly accurately, even those like far away objects. And also the map segmentation result is also fairly good. Although you can see some blurry like before the intersection, but that's mostly because we don't really have the information at that region. There's some occlusion and a limited sensor coverage in some regions. For example, you can see the top right corner of this visualization. Then let's take a look at the quantitative results of the 3D object detection on the nuScenes. So there are a lot of numbers here. Before looking at the numbers, let's first take a look at the metrics that we care about. So first is the modality, basically which sensor, what are the sensory like inputs the method uses. And then the next two is the number of flags and the latency. So these two are the efficiency measures of a model. So the number of flags is the hardware agnostic measures, basically counting the number of multiply adds in the model. And the latency is measured on RTX 3090 GPU. And the rest 4 here is the MAP, NDS on both validation and test set. The MAP is the 3D object detection accuracy. And the NDS is an aggregated detection score defined by the nuScenes leaderboard. So it's kind of, it also cares about some other factors like attribute estimation and also the velocity estimation. So let's first take a look at the camera-only baselines and the LiDAR-only baselines here. So one thing we can clearly see is that accuracy of the LiDAR-only baseline detectors are much higher than the camera-only baselines. So the reason for that is the 3D detection is a task cares about the geometry of the scene and objects. you can directly get an accurate spatial estimation from the LiDAR sensors. While for the camera sensors, it's actually very hard to get the spatial estimation, the depth estimation. So that's why there's a huge gap here. And then let's take a look at the sensor fusion methods. So we compare with a few representative sensor fusion methods, the point painting we have just introduced, and some others like MVP, filter 3D, transfusion. But one thing we can clearly see here is the sensor fusion method typically is more expensive, computationally expensive compared with the LiDAR only method. For example, you can see here the filter 3D uses like 1T max, while for the center point, the LiDAR only center point is only like 150 G max. In comparison, our BEVFusion is able to achieve the state-of-the-art performance while actually being much, at least 1.5 to 2 times more efficient than those baselines here. Another thing we can see here is compared to LiDAR-only baselines, the fusion method like BEVFusion, right? It achieves a very high accuracy, a large accuracy improvement around 10% on the validation set and more than 10%, around 10% on the test set as well. So we want to understand where these improvements actually come from. So here we study some the performance of our BEVFusion, the LiDAR-only baselines, the baseline sensor fusion methods under different object sizes and object distances. But one thing we can clearly see here on the left-hand side is that the BEVFusion achieves a very consistent improvement over the LiDAR-only models across different object sizes. While for the MVP, it only achieves a good improvement for the smaller objects, but for the larger objects, the improvement is actually very marginal. Sorry, the other side. Achieve a large improvement for the larger objects, but for the smaller objects, the improvement is actually very, very marginal. And also from the right-hand side, we can see, compared with the LiDAR-only method, our BEVFusion achieves a much larger improvement for those objects that are very far away, distant away from the Eagle car. That actually makes sense because the LiDAR has a very limited coverage, range coverage. So that's something can be improved by the dense camera information. So you can actually bring a much larger improvement for this case. And then let's take a look at the results of the BEV map segmentation. So the same here, we first take a look at the metrics. We care about the mean IOU here, and also the per class IOU scores for all these different semantic classes. And the camera-only baseline, the LiDAR-only baseline. So we actually have a better camera-only baseline already. The BEVFusion C is a camera-only variant of our BEVFusion. It already achieves at least 12% higher MIOU compared with the previous camera-only baselines. Well, one thing that's very interesting here is you can see the LiDAR-only method performs much worse than the camera-only models. That's directly the opposite from what we have just observed on the 3D object detection. So the reason for this is this task is more about the semantics rather than about geometry. So this is actually this type of information is what the camera can help the most. And then finally, the fusion results. So compared with the baselines, the point painting and VP, they mostly just care about objects. So that's why they don't really have much improvement compared with the LiDAR only baseline here. There are marginal improvement around 0.5%, while our BEVFusion achieves a much larger improvement, around 6% over the strong camera only baselines here. All right, so that's enough for the numbers for now. So let's take a look at how robust our fusion model is to different lighting and different weather conditions. So because of the limitation of the nuScenes data set, we can only test the performance under the nighttime and daytime and rainy days and sunny days. So let's first take a look at the lighting robustness. So poor lighting conditions are very challenging for the camera-only models because camera provides less information during the night. So the camera-only LSS, so the camera-only baseline here, performs much worse during the nighttime. It actually has a 25%, at least 25% MIOU degradation. While with the fusion, with our fusion, the BEVFusion can significantly boost the performance by around 13%, which is the improvement is actually even larger than what we got for the daytime. So this actually demonstrates the significance of the geometric clues when the camera sensor fail. And this is the visualization of the camera-only baselines during nighttime. You can see it cannot recognize the objects, like the faraway objects here, and also the segmentation quality is fairly poor. While for our BEVFusion, it's able to recognize much more objects on the data, and also the segmentation quality is much better here. And then let's take a look at the results under different weather conditions. So detecting objects in the rainy weather could be challenging for the LiDAR-only method because of the sensor noises during the rainy days. So the LiDAR-only detector's center point here, you can see it has around 4% accuracy drop compared with the results during the sunny days. While with the BEVFusion, you can see it improves the center point by 10.7%, actually achieving slightly better accuracy than the sunny days here. So this is because the camera is actually very robust to different lighting conditions. So adding this information to the fusion model can help a lot. So some visualizations here as well. So this is the LiDAR-only baseline. The segmentation result is clearly very blurry, and this is our results. So you can see the lane dividers are much clearer here. And also we studied some effectiveness of our BEVFusion under sparser LiDARs. So the reason why this setting is very interesting is the sparser LiDARs are usually cheaper, so it can be actually deployed, more deployable or affordable on the cars. So for example, a 4-beam LiDAR consumes around $1,000, while for the higher end LiDARs, they can be much more expensive. So BEVFusion brings a much larger improvement for the sparser LiDAR. For example, for the 1-beam LiDAR here, the improvement is around 12% compared with the MVP. It makes sense because the LiDAR is very sparse, right? The point painting or point decoration will drop almost all the camera features. This is clearly not optimal. And radars can be seen as a sparser variant of the LiDAR. So we also did some analysis on the radar, camera radar fusion as well. So here the baselines are the center fusion, the filter 3D, and the recent result called Craft. So you can see that compared with these baselines, the BEVFusion can at least deliver the same detection accuracy, which is the MAP here, and achieving much better velocity estimation. So here the MAVE is the mean average velocity error. So it's the lower the better. And the NDS is the aggregated scores. So you can see the BEVFusion can achieve this result with at least 3 times faster compared with the baselines. And recently we also tried to accelerate this model using TensorRT. We can achieve around 40 frames per second using the same model here. And finally, let's take a look at some leaderboard results. So BEVFusion ranked first on the nuScenes 3D object detection as of last summer. So as I mentioned earlier, this is a very fast evolving direction. So they're having a lot of works coming on the leaderboard in the past 1 year. But some of them are actually using very similar approaches as BEVFusion, some follow-up works. And BEVFusion also ranked first on the nuScenes 3D object tracking benchmark. So tracking is one step further than the detection. So we not only want to detect those objects, we also want to associate the same objects across different frames. So this is actually very necessary for doing motion prediction, even in the later planning series, also very crucial. And also on the Waymo 3D object detection benchmark, Argoverse benchmark. And we have open sourced the code of our BEVFusion on the GitHub. So it has received 1,000 stars since its release, and feel free to check it out if you're interested. So that concludes the first part about the BEVFusion. So there are 2 main key takeaways here. First, the bird's eye view space is actually an ideal space for the multitask multi-sensor fusion. And secondly, the view transformation actually plays a crucial role in terms of the efficiency and should be properly accelerated. And before move on to the next part, I would like to pause a little bit to take some questions you may have. Yeah.
I just have a question on your prefix sum.
Okay. Prefix sum.
If you write a kernel for each cell, basically, right? Each cell,
Mm-hmm.
then you have to make the cells equal length, right? How often equal length?
It doesn't have to be. Like some threads might like finish the job earlier.
So if you push all of them to the GPU, you have to integrate zeros when they're not equal.
You don't have to. You just need to mark the starting and ending position of each interval, and then you can just assign the workload to like each GPU thread. So for some GPU thread, like their workload might be lighter, so it can finish like earlier, but it's also fine. So it's kind of bottleneck by the interval that has the heaviest workload.
Yeah. So even if they finish earlier, they will still wait till the last one finish.
That's kind of right, but like there are some other like optimizations we can do here. For example, if it's highly imbalanced, right, we can kind of group some of the.
So this one to this part, this one.
But we haven't done that because like in reality, like the actually it's fairly like equally distributed. Yeah. Are there any other questions? Yep.
So just in general, what are the outputs of these different types of models?
So yeah. Let me find a slide here. Probably not this one. So the output is like the detection and the BV map segmentation, right? So yeah, probably this one. So for the detection, you just generate 3D boxes. So for each box, you have the 3D positions, the XYZ. You have WHL for the 3D sizes. You have the orientation, the heading orientation, and also you have the velocity prediction. For the BV map segmentation, it's basically generating a multi-class like prediction for each of the pixel here. For example, for each of the pixel here, we will generate a probability vector over like let's say 10 different classes and one for each semantic class.
How do you know the velocity of the objects? Are you combining multiple frames together from sensors, or is that fusion happening in a separate?
Yeah, that's a very good question. Right? You can see here the BV-DET is a camera-only model, so you can see its velocity estimation error is very large. So the unit here is like a centimeter per second, so it's like 1 meter per second error, right? That's a very large error because it's a single frame model, so you cannot really estimate the velocity from the single frame camera model. It's basically guessing the velocity based on the class. But radar can directly provide the velocity estimation. But for the camera LiDAR fusion models, because we usually use like a 10-frame LiDAR aggregation, so we'll map the LiDAR point cloud from the previous frames and transform it into the current coordinate system and then just like fuse them together. So we will also have the information for that. So one thing we can see here.
That was the reason why you have this car image with red dots. There are multiple red dots for each.
Yep, that's right. You can also see here, there's a trace here, like behind the car. When it's not moving, you cannot see it, right? But as long as it's moving, we can wait a little bit. Yeah, you can see there's a trace here, right? That's because we're aggregating the LiDAR point cloud from multiple frames together. But if it's not moving, then you're actually stacking the same point cloud over and over. Are there any other questions? The training pipeline is actually a little bit complicated. We need to first pre-train the camera encoder, and then we pre-train a LiDAR-only model, and then like fuse them together. So the camera models also go like these like a few steps of pre-training, because if you want to get a good result on a leaderboard, you usually need to like use a lot of like complicated training tricks, like first pre-train on the ImageNet, then on the Coco, and then on the new images. Yeah, a lot of steps in order to get a good result. But like, I don't think this actually matters if you have a larger data set. So I would say like in general, if you want.
nuScenes is already really large. Because I guess it's not that large.
It's larger than some like data sets, but like for example, it's definitely smaller than ImageNet, right? Yeah, the Waymo data set. So we have to go through all these pre-training stages. But like in theory, I don't think these actually matter as much as long as you have a larger data set.
I know. From a researcher
So in total, I would say 2 to 3 days on 8 GPUs. Yeah.
Are all the intermediate models fully convolutional, or are there parts of the models are they that have other architectures and then?
Yeah, let's go back to this slide. Yeah, so for the camera encoder here, we're mainly using like swing transformer. But for the camera radar fusion, because that one we target deployment, so we're using ResNet. The swing transformers are harder to deploy. And for the LiDAR encoder here, we're using a voxelnet. I will explain what is voxelnet in a bit. So it's basically a model composed with like sparse convolutions. And the radar encoder here is the point pillar. So basically a few MLPs on each point cloud. On each of the point. And the BEV encoder is just a convolutional neural network. Yeah. Yeah, the other parts I don't think, yeah, they're mostly like non-parameterized. So
in principle, if someone wanted to retrain your DEV, they wouldn't have to retrain a new model from scratch. They could use your weights.
Yeah, exactly. Especially we have actually released the camera pre-trained weights and also the LiDAR pre-trained weights, so you can directly reuse them. Yeah. All right, then let's move forward to the second. Oh, sorry.
Sorry. So I have a kind of amateur question, which is for this bird's eye view fusion. What about thinking about the case that the car is driving on a road, which is have a drastic change of raw and feature? Is it also works in your algorithms? Because most of the intensives you're using in the slides are just a city, lots of cars, but actually the road is just a plane.
Yep.
Yes,
so if there's an elevation change or something like that, right? Yeah, that's a good question, especially if you're applying that to, like, for example, San Francisco, right? You can definitely see like a huge elevation change. I think that's a good question, actually. So because I briefly mentioned that before, like even though we are projecting the data to the bird's eye view, it's in 2D, but the high dimension is not necessarily lost because we actually will squeeze the high dimension into a channel dimension. So that way it's kind of still preserved. But I definitely agree, if you want to deal with such cases, I think not necessarily bird's eye view, you can make it like a bird's eye view, but with a few like beams on the z-axis, for example, 4 beams or 8 beams. We have tried it on the nuScenes. It doesn't work as well. Probably it's because like the reason you mentioned is mostly flat. But for like the cases that there's a drastic elevation change, probably that could be useful. Yeah.
So this kind of orientation changes also can be regarded as a feature.
Orientation, you mean the elevation changes or
Yes, aviation or this kind of information.
If you have the map, then yes, because if you have the map, the way you project it to the bird's eye view will be projected onto the road rather than the really discarding the Z, right? But it's usually harder to actually get that. But if you have an HD map, probably you can achieve this. Yeah.
So we'll go to the second part of our.
Yep. Oh, sorry. All right, let's continue. So the next one I would like to share is Flatformer. So let's first revisit the latency breakdown of the BEVFusion. So this is the breakdown after like we use the optimized view transformer. So you can see the view transformation only takes around 12% of the runtime here. So after this optimization, the latency bottleneck becomes the LiDAR encoder. It takes around like 43% of the total runtime. So that's what we'll be focusing up next for acceleration. So let's first take a look at the 3D object detection benchmark here. It might not be very easy to tell from their method names, but actually all these highlighted ones are based on sparse convolutions. to build their like LiDAR encoders. So what is sparse convolution? So conceptually, it is actually very similar to the dense convolution being applied to the sparse data. So here, the left-hand side is the dense convolution, and the right-hand side is the sparse convolution. So for each of the output location here, we just draw a 3x3 window surrounding it, and then we do the convolution, basically multiply each of the element here with the corresponding weight value in the convolution. So for the dense convolution, even though there are a lot of values, zero values in the window here, we still need to compute all of them, do all the matrix modifications here. While for the sparse convolution, we'll skip all those like zero neighbors so that we can reduce the computation cost. So this is like especially very useful for those sparse data, for example, the LiDAR point cloud, where the sparsity can goes up to 99%. The other difference you might have already noticed here is the sparsity pattern is different after the convolution, right? So for the dense convolution, an element is non-zero as long as one of the elements in a window is non-zero. So for example, for this output point, we have one of its values in the window is actually non-zero, so it's actually non-zero after the convolution. While for the sparse convolution, it is non-zero as it is zero as long as the input is also zero. So this design is more from a practical consideration because we want to keep the sparsity like rate so that we can use that, leverage that for the acceleration. If we follow the same design as the dense convolution, then after a few layers, we'll basically have no sparsity at all, right? So the support for the sparse convolution is actually highly non-trivial because we need to write specialized kernels for it on the GPUs. So this is because the sparse operators are not naturally supported on the GPUs. They are actually not favored by the GPUs. So we have built a library called TorchSparse to help resolve this issue. So its API is very similar to the PyTorch. If you're familiar with that, you can see from the right-hand side. So basically, for the model definition, you only need to replace the torch.nn with our tsnn. And for the tensor, you replace the original PyTorch tensor with the sparse tensor. So after that, you can just use the model and the tensor as if they're like PyTorch models and PyTorch tensors. So you can do the forward here, you can compute the loss, and do the backward here. So the installation is also very simple. It's just a one-liner installation. So feel free to use it if you're working on some sparse convolution-related stuff. So the library is highly optimized. So compared with the industry-leading solutions from NVIDIA and from TuSimple, so our TorchSparse is up to three times faster for the inference and around 4 times speed up for the training benchmark. So it's highly optimized, but you can probably imagine there are a lot of engineering efforts behind that. So it becomes very challenging if you want to support more hardware. Right? For example, if you want to support other hardware other than the NVIDIA GPUs, like AMD GPUs or on the Qualcomm devices, then we need to go through all these optimizations over and over again. So the question we keep asking ourselves is it possible to redefine the computation for the sparse point cloud so that we can reuse these dense operators, and then we can reuse all the efforts people have already spent on the optimizing these dense workloads. So that's why we started to look at the transformers. So transformers are actually very popular these days. For example, it's actually used in the latest ChatGPT. So let's firstly quickly revisit how the transformer works. So this is the architecture of the original transformer model. We can just focus on the left-hand side, which is the transformer encoder. So you can see there's a multi-head self-attention, which is the key operator in the encoder. And we have the feed-forward network, which is basically applying the MLPs over all the points and having some skip connections here and normalization here. So for the multi-head self-attention, this is the diagram of this. So basically projecting the input sequence into values, keys, and queries, and then use the scale dot product attention to process it. So here's the definition of the scale dot product attention. It's a little bit complicated. The formulas are not very easy to understand at first glance. So the key idea here is to compute a correlation between the keys and queries. So between each two tokens. So this is the correlation matrix you will get, the softmax QK here. And then you use that as a weighting factor to weight all the input features, the V here. then you will get the output. So the transformers have been very successful even outside the domain of natural language. For example, people have applied it to the image domain as well. Here we have the vision transformers. So the basic idea is we split the images into fixed size patches, like 16 by 16 patches, and then we just treat them as a sequence of tokens, as if it's just like a sentence. And then we can use the transformer layers to process it. So it works surprisingly well, actually. So it's performing like on par, or sometimes even better than the convolutional neural networks on the image benchmarks. And it has also been extended to like video as well here, and also to the audio domain, the audio processing here. So however, transformers are not as effective for the point cloud. So here's a trade-off curve on the Waymo open dataset. So the x-axis is the latency, and the y-axis is the mean L2 MAPH, so basically a 3D detection accuracy metric. So you can see that these two gray methods are center point and center point plus plus. These are sparse convolutional models, and the other ones are the point cloud transformers. So the point cloud transformers start to catch up in the accuracy side, but the latency still lags far behind, like around 3 to 4 times slower than these sparse convolutional models. So why is this? Let's first take a look at the most straightforward approach of implementing the point cloud transformer. It's called global PCTs. So the basic idea is just we treat all the points in the point cloud as a 1D sequence, right? And then we just use the multi-health self-attention to do some token mixing, and then using the feed-forward network to do some channel mixing. So the issue of this approach is that the time complexity of this model is actually very high. We can take a look at the time complexity for the multi-head self-attention here. It's actually quadratically related to the number of points. So for the single object, this could be tolerable. For example, if we only have 2K points for a single object, the latency of a single layer point cloud transformer is around 3 milliseconds. Well, if we're going to scale up to the outdoor scenes where we can have 32K or even more actually, the latency could be as far as just 1 second for one layer, not to mention if we want to stack multiple of them together to build the actual model. So because of this, so most of the recent point cloud transformers actually follow a different approach. It's called window PCTs. So the basic idea is we want to apply the transformers only to the local regions. So to achieve this, they will first split all the points into like non-overlapping windows here. So for example, in this visualization, we're using 2 by 2 windows. And then for each window, we just apply the multi-head self-attention within the window. So that way we can reduce the computation cost a lot. So after the projection, we have C, AE, HBG, IFD, these 5 groups. So one key challenge here is different from the 2D images where like all the elements are there. So it's basically highly regular in like across different windows. But for the sparse point cloud, if you take a look at the distribution here, for some windows you like around 20% of the windows actually, you have only like 1 point here. While for some windows you can have as many as like 81 points. So there's a huge imbalance in the workloads different windows are processing. So because of that, we cannot actually use a batch computation for all of them. So the way people usually do is we do some like adaptive grouping. So basically grouping those windows with similar workloads together. For example, here, the C, AE, IFD, these 4 groups windows are grouped together. And then we'll pad some zeros to make sure that all the workloads within the same window is actually balanced. And then we can apply the batch computation for each of the group here. So it's very effective actually in improving the hardware utilization. But the problem here is that you're introducing a lot of overheads. We don't really need to compute the multiplication for these zeros, but we have to pad them to make sure the workload is balanced. So the key idea of our platformer is how about we just make the workload balance at the first place? So the way to achieve this is we first flatten the point cloud into 1D sequence. So the way we do the flattening is do a window-based sorting. So basically means we go over each window from top to bottom, from left to right. So basically the first window is C, and then AE, HB, G, IF, and D. So this is the flattened sequence we get here. And then after that, we just partition those points into groups of equal sizes. So in this illustration, we're just using a group size of 3. So that like after this step, all the groups have perfectly regular workloads. So we can use a batched computation over all of them. So there's a caveat here. So there's no free lunch. Like the computation regularity is perfectly regular, but you can take a look at the spatial regularity of different groups. So you can see for some groups, for example, the final group, the IFD, they are not spatially contiguous on the memory. So on the in the 3D space. But we were showing in a few slides that this is not a big deal because the self-attention has the capability to suppress these outliers. And there are a few other designs here, like we do the sorting axis alternation and also do the window shifting. So the reason for that is I mentioned that we're like doing the flattening using a row major sorting, but that actually breaks the symmetry between different axes. So what we do is we just alternate the sorting axis across different transformer blocks. So the first one we're doing a row major sorting, and the second one we're doing a column major sorting. And also we use the shifted window. The idea is to just shift the window by half of the window size. So these two techniques are used to encourage the communication of the features across different like directions and also across different axes. So then let's take a look at the latency results here. So here the latency is measured on the A6000 GPU. So you can see the center point is actually a very strong baseline. So these two are the point cloud transformer baselines. So it's like 2 to 3 times faster than the point cloud transformers. So by just changing the grouping strategy from the equal window grouping to the equal size grouping can directly optimize the latency by a lot to 20.5 milliseconds, although it's still slower than the highly optimized center point with the sparse convolution. But one benefit of the platformer is it can reuse all the efforts people have already done for the dense operation optimizations, right? So here we just used a few optimizations people use for the transformers, for example, replacing the attention with the flash attention. That's a very popular implementation. The basic idea is to just fuse all the attention operators into one GPU kernel. This directly improves the latency by a factor of 1.7 times. And then we did some other optimizations like packing the matrix modifications, fusing all the kernels in the FIFO networks. So these two are actually very common practice by the dense transformers. And finally, we'll drop the last group if there's any residual points. So all of these can bring us another 3 times speed up compared with our baseline implementation. And it's also much faster than the center point here. And then let's put it back to the trade-off curve. So that's what we got after all these optimizations and accuracy evaluations. So its accuracy is much better than the center point. It's performing on par with the very strong center point plus baseline here, and also closing the 3 to 4 times latency gap between the point cloud transformers and sparse convolutions. And here are some analysis of different grouping strategies. So as I mentioned, the baseline is using the equal window grouping while we're using the equal size grouping. So the equal window grouping is also performing pretty well. While we did a few things here, so the first thing is the sorting criteria. If we don't do any sorting at all, just randomly permute the point cloud, its accuracy is actually very bad. And because it actually breaks the spatial locality. While if we do not do it in the window-based manner, it's also hurting the performance a bit. And finally, the axis alternation, you can see, and the window shifting here also improves the accuracy a bit. And here are some visualizations of our grouping strategy. So here, different colors represent different groups after the partitioning. So you can see for some groups, actually the entire group located in the same object is fairly local. While for some groups, for example here, right, actually the points within the group actually spread out over a fairly large region. But that's not a big deal. Let's take a look at the attention visualization here. So here, different colors represent the weight of the attention. So the red color represent a higher attention and the blue color represent a lower attention weight. Let's take a look at the same example here. For example, for those outliers you can see, right, actually their attention weight is fairly low. So that means even though sometimes the grouping strategy is not like perfect, but the self-attention mechanism can actually deal with this type of outliers very well, just suppressing their weight, attention weight in the computation. And finally, let's take a look at the deployment results. So we have deployed our platformer on the NVIDIA Jetson AGX O-ring. So you can see here, it's the first point cloud transformer achieving the real-time inference on the hardware. Like the real time is like defined by 10 frames per second. And it's also much faster than the center point. So right, that concludes the second part on the platformer. So two key takeaways here. So first, the computational regularity is actually very important. It's even more important than the spatial regularity. And second, efficient implementation is actually very important to exploit the full potential of the transformer. So I will pause here again a little bit to take some questions. Yep.
So that means you don't actually need the whole car to detect the car. You need part of the car.
Kind of, right? But after some window shifting and axis alternation, even if the original grouping is like just part of the car, right? You will actually get some features from other groups as well. So actually, at the end of after the encoding step, maybe other points within a car will have the feature of the entire car, so you can use that to detect the car. Yeah. Is there any other question? Yep.
Do you think that that it's in terms of your conclusions that the computational regularity is more important?
Mm-hmm.
Do you think that just trading off like sort of efficiency allows you to train much faster? So it's not necessarily that the architecture is better, but maybe with more and more training, the sparse architecture could be better. I mean, if the inference was just as fast.
Yeah, that's right. So like the takeaway here is like sometimes you want to do some approximation so that you can make the workload faster. So those approximations sometimes is fine because it can be compensated by a better algorithm design. For example, the self-attention is actually very robust. These neural networks are actually very robust to those kind of approximations, right? And also, if you think about it, right, why the window has to be defined in a regular way at the first place? Why it has to be by 2x2 windows or 9x9 windows? Why can't we just do that in this way or other ways, right? So one thing we found, like for the point cloud processing, is sometimes the way you define a neighbor doesn't matter as much, as long as you gather some information from some local neighborhood. So for example, like before the sparse convolution, there's a stream of working on PointNet plus. They're actually like defining the neighbors based on using some k-nearest neighbor query, like on the L2, using the L2 distance. And then the sparse convolution using a grid-based neighbor query. So that means like the definition of the neighbor actually is not the most important thing here, right? But if you can relax the definition of the neighbor while getting a better efficiency, that could be something we want. So that's, I think, the main takeaway of the platformer work here. Yeah. Yep.
So a follow-up to that.
Yep.
In the first transformer layer, or in the first voxel convolution layer, the signal is sparse because you only have features at each point. But then when you get to the next resolution, do you still have much sparsity, or at that point do you lose that? Because I'm assuming that per like individual 2x2, 3x3 cell, you're gonna have less.
Actually, in this work, we didn't do any downsampling. So that means the point cloud is the same across the whole model. But if you do some downsampling, yeah, probably after a few downsampling, you might having denser and denser point clouds. That could be the case.
Well, what I was asking is, I'm assuming there were multiple layers of the
Yep.
transformer.
Yep.
So I was essentially wanted to know how do the next layers look like? You had a picture where you split up the.
Let me go back to that slide. Here, right.
Right.
So this is the input, right? And then after one layer, it will still, basically it's still in the same representation as the input. But like in the next block, maybe we're using a different sorting axis, so the partition will be different. So the order here might be different in the next block.
Okay, so you're essentially starting with something that's regularly sampled at that point, and then you come back to something that's sampled at those same points.
Yep.
So you don't change the sampling point.
That's right. We are still we're always keeping the same points throughout the model. Yep.
So I have a question on the window shifting.
Yep.
Can you explain again how does it work?
So the window shifting here is basically for, let's say for the first block, you're using this window like partitioning strategy. So starting from the top left corner here, and using a 2 by 2 window to split the.
I thought you were discarding the window.
But the sorting still happens in the still happens in the window manner. So we flatten it, but the way we flatten it is based on the window, because we want to make sure it's kind of like more regular in the spatial wise. We actually have the ablation study show that if we don't do that in the window level, if we just directly store the coordinates here, for example, in this example, you'll get A, C, E, H, B, I, G, F, and D, right? If you do it that way, it actually hurts the performance a lot.
Have you tried rotating the thing?
We actually tried. We tried to rotate it by 45 degrees, but we found that actually if you have both X and Y axis, then it's sufficient. So because if you think about it, you can like, if you want to propagate the information to a 45 degree, you can do that in two layers, right? Yeah. Yeah. Are there any other questions? All right. Oh, sorry. Okay. Yeah, so I will give a high-level overview of the final work called Sparse ViT. So the paper is available online, so if you're interested in more details, you can check it out on our project website. So let's take a look again at this latency breakdown here, right? After we optimize the LiDAR encoder, so the secondary bottleneck is actually the camera encoder. But why is the camera encoder slow? Right? The resolution is actually the key factor. So here's the trade-off, the accuracy, detection accuracy, and the latency using different image resolutions. So in fact, most of the state-of-the-art 3D detectors are using very high resolution to achieve the high accuracy. So as you can see, the accuracy gap between the highest resolution model and the lowest resolution model is around 10% actually. But again, there is no free lunch. The accuracy comes at the cost of the huge, cost on the efficiency side. So the latency is also around 10 times larger than the lowest resolution models. So from this, so the question here is there a way that we can keep the fine details from the images? Because the reason why we want to use the high resolution to achieve high accuracy is because the high resolution can help us keep those fine details, for example, some small objects that are far away from the ego car, right? But is there a way that we can still keep those fine details, but at the same time, we can reduce the number of pixels, where we don't really keep that many pixels from the images? Does anyone have any idea of how to achieve this? Sorry? Fourier domain information. So that's actually sparser, right? But the challenge here is how to design the CNN that could be very effective for the Fourier domain. Yep.
Perhaps you could first process the low resolution image to see which points are interesting, and then based on that, hierarchically process the high resolution image.
Yeah, that's actually a very interesting idea. We have a ongoing work actually exploring similar ideas of that. So because compared to the low resolution image, right, the high resolution image probably just contribute a little bit to that. Like for example, for some boundaries, for some small objects, but we don't really necessary to keep all the images in the high resolution. Probably just part of that, right? So that's actually a very, very interesting idea that probably the paper will come out soon, but yeah. Yeah. Does anyone have any other ideas? Yeah, so in this paper, the Sparse ViT like explore the activation pruning to, so there are other options for sure, but like this paper explores the activation pruning to solve this. So the key motivation here is very similar to what you have just mentioned, right? Not all the pixels are equally important, especially for different tasks. The importance for different pixels could be very different. For example, if you care about the 3D detection here, probably we only need to keep those pixels that relate, like corresponding to like an object, while we can discard all the other like background pixels. So then after that, the intuitive idea is just to simply prune those like non-important pixels to get some acceleration. So here, the upper image is obtained by just directly downsampling the image by 2 times, while for the lower image is obtained by keeping the resolution the same, while pruning away like 75% of the windows. So that means the upper and the lower images, they are essentially having the same number of pixels. But we can clearly see that the lower image preserves more details. For example, for these pedestrians, right, you can better recognize them from the higher resolution but sparser data. So this is an overview of the Sparse ViT. So the high-level idea here is we want to prune the activation, those like blocks that are not very important to the task. So one thing we did here is like we prune the all the pixels in a blockwise manner. That means we either prune the entire block or we keep the entire block. The reason for that is if we do a fine-grained pruning, for example, like we can prune any pixel we want, that could make the whole workflow very irregular. So we need a lot of optimization like techniques to support that. But if we do that in a blockwise manner, and also actually the recent window-based transformer is already executed in a blockwise manner, that could directly gives us some like speed up on the hardware. And also like how we define the importance. So we don't want to do a manual, like have a manual rule to define the importance. For example, some pixels are more important, some pixels are less important. The way we do that is to learn it end to end. So basically we just use the activation, the L2 magnitude of the activation of each window as the importance measure, so that the model can learn that, okay, if this block is more important, we probably will give a higher activation values to that. But if it's less important, probably like fewer, like a lower activation value for that block. And another thing we explored is we use different sparsity like levels at different stages. For example, for the first few stages, we might want to use lower sparsity while we can gradually increase the sparsity value. The reason for that is different layers have different sensitivities. For some layers, they're very sensitive. For example, those are like closer to the input, sometimes it could be very sensitive. Closer to the output, that could be very sensitive. So we try to optimize the sparsity configuration for the model using an evolutionary search and to find the best one under different constraints. Yeah, there are a lot of other details here, but you can, if you're interested, you can take a look at our papers, a lot of calculation, some more details on how we determine like the sparsity ratio for different layers. So let's take a look at the visualization here. So these are the original images before any pruning. So the Sparse ViT actually learns to prune those background pixels. If you're training that using a 3D object detection, it automatically learns to just prune out those background pixels. Here it keeps those pixels related to the pedestrian here and those pixels for the cars here. But if we are using a higher, even more aggressive pruning strategy, the Sparse ViT will learn to keep what matters the most. For example, here it keeps the barriers and also the far away cars here, because these two are actually the classes this data set cares about: the barrier, cars, pedestrian, all these classes. And as a result, the Sparse ViT can achieve 1.5 times speed up compared with the baseline on the hardware. And also, it's achieving a much better accuracy latency trade-off. Well, I forgot to mention, so for the accuracy latency trade-off, we want to push the method to the top left corner. So if it's somewhere here, it's like better. So you can see that it's definitely achieving a much better trade-off compared with the baselines just reducing the the width of the model or reducing the resolution of the model. So that's a very brief overview of the sparse ViT. So 2 takeaways here. So first, not all the pixels are equally important. And for object detection, we might care more about those foreground pixels. But for map segmentation, we could actually care more about those background pixels. So the definition of the importance should be learned automatically with the model training. And secondly, the sparse high-resolution features are more informative than the dense low-resolution images. So that means instead of directly downsampling the image, why not just prune away those unimportant pixels from the image? And then the most relaxing part of the lecture, some deployment results. So this is a video of the autonomous racing vehicle of the MIT driverless running on the track of the Formula Student Germany competition. So the goal of the competition is to build an autonomous system that can run autonomously on the track and finish the track fast and safely without hitting any traffic cones. You can see there are 2 different colors of cones on the track, actually marking the drivable space of the car. So together with the engineers at MIT driverless, we have replaced. We replaced the original 3D perception system with our model. You can see the original model already achieves a fairly good accuracy, 95%, while our model delivers an even better accuracy and also reducing the latency by 4 times. So with a more accurate model and a more efficient model, the car can see further and drive safer and faster. Oh yeah, it's actually not a very low-end GPU though. So it's yeah, I think it's on a 1080 or something. I forgot the exact.
Are you considering this is not the whole pipeline, right? It's only the computation. Like from image capturing to the.
Yeah, so the latency here is only about after you receive all the sensory data. So there are some processing or sensor the data capturing time. Yeah, that's excluded in the latency measurement here. So apart from the racing car, we also have a collaboration with MIT Distributed Robotics Lab. So to deploy our model onto a full-scale autonomous car. So here's a demo video. So you can see here the car is driven autonomously based on our 3D perception system. It's tested in a closed environment because of some regulation concern, but you can see it's driving fairly smoothly. And also we tested its performance of navigation. For example, just giving the navigation map here, it learns to turn left, turn right, or just going straight. Yeah, and also finally, we have also tested its robustness under sensor failure cases. For example, you can see the left-hand side, after a sensor failure, you directly need to intervene, while for our model, it's able to recover fairly robustly. All right, so that's all I have for today, and I'm happy to take questions if you have any. Thank you.